Now let's look at the IoT data protocols and architectures. The efficacy of an IoT system depends to a great extent on the interconnection between many different types of things, which may have different communication, processing, storage, and power supply characteristics. Table 1 shows a list of 9 data link protocols widely used for data transport in IoT systems. So this is Table 1. So you may have found many familiar names there, including Bluetooth, the Zigbee, the NFC. We also talked about Sigfox and LoRaWAN cellular before. Example protocols used for short-range and local-area wireless network include Bluetooth, Zigbee, Z-Wave, Wi-Fi, and NFC. They are often used to transmit data over short ranges from 10 centimeters to 10 meters to 100 meters. In addition, there are long-range and wide-area network protocols such as Sigfox, Neo, LoRaWAN, and cellular communication technologies. These technologies are commonly used for smart cities and environmental applications to transmit data over ranges from 2 kilometers to 200 kilometers. The IoT system also uses the internet to connect a large number of things. Internet Protocol (IP) is a universal standard for data communication over heterogeneous network. Each thing is assigned a unique IP address. As the number of things connected to internet is increasing rapidly, scalability of the protocol has emerged as a major challenge. So currently, we are using our IP version 4. It is a 32-bit address system. Now, the whole world is moving towards IP version 6. It is a 128-bit address system that can provide that many addresses, 3.4 multiplied by 10 power 38. So it's basically it is a large number beyond imagination. So it can enable every IoT thing to have a unique IP address in the global internet network. 6LoWPAN is a key IP version 6-based technology defines encapsulation and header conversion mechanism independent of the frequency band and physical layers. It can be used across different communication platforms, thereby enabling sensors in heterogeneous network can carry IP with 6 packages and become part of a large-scale IoT system. Specific to manufacturing, MT-Connect provides an information model that includes both a common vocabulary and semantics for manufacturing data, as well as some communication protocols, specifically through the agent. So it was developed by the MT-Connect Institute to enable manufacturing equipment to communicate data and exchange information using standard internet technologies, so including HTTP and XML, rather than other formats. In other words, MT-Connect is a universal protocol for communication between IoT-enabled machines and user-specific applications in the manufacturing shop environment. In other words, open standard grammar and vocabulary are provided by manufacturing directory and XML models to define and model manufacturing things, such as names, units, values, and contexts of the machines and cutting tools. Notably, Table 1 lists a variety of protocols that can be used to connect and control things remotely. However, MT-Connect is just a read-only communication protocol that ensures safety by design. In other words, software applications can only request data from MT-Connect compatible things, but cannot control the machines or equipment through the MT-Connect standard. As shown in Figure 2, MT-Connect consists of 3 basic components: adapter, agent, and application. The adapter is a software tool that links and converts various data definition to MT-Connect data definition. The agent receives data requests from applications and then uses the directory, dictionary, and semantics to transfer raw data into MT-Connect compliant data. So it's very straightforward in this way. Furthermore, MT-Connect compliant data will be transmitted to the application for information processing and knowledge discovery, including data requests, storage, analytics, and visualization. If the data follow MT-Connect definition, then there will be no need to redefine data for every MT-Connect compliant software application. In addition, a number of IoT frameworks and architectures such as RAMI 4.0 and OPC Unified Architecture have been proposed to define the communication structure of IoT 4.0. So we talked about the OPC Unified Architecture before, and RAMI 4.0 provides a reference architecture model to define the three-dimension map for Industry 4.0. However, there are also other IoT architectures currently available. So it is difficult for all companies to use the same reference architecture of Industry 4.0 due to competition in the business world, because everyone wants to take lead in the field and they develop their technologies and try to make the technologies as the standard. So that will make them a lot of money. As with the first phase of internet development, it is anticipated that the competition and collaboration will eventually result in a widely used IoT framework and architecture for Industry 4.0. Table 2 shows a list of major IoT platforms and their characteristics. IoT platforms provide the software infrastructure to enable physical things and cyber world applications to communicate and integrate with each other. Examples include the GE Predis, ThinkWorks, IBM Watson, Azure, Deep4IoT, and Amazon Service. So you may have heard of these names somewhere already. So most IoT pervasive IoT sensing leads to the proliferation of data. Most IoT platform provides a service called dashboard for data visualization. So currently, dashboard programming has become popular in IoT because it provides an easy, user-friendly graphical user interface to monitor key performance indicators quickly and generate reports for decision support. So, for example, the Azure is from Microsoft, I believe. It has such functions. However, most of these platforms are limited in their ability to fulfill the needs to realize smart manufacturing. In short, these platforms are not specifically designed and customized for the manufacturing industry. It is critical to integrate manufacturing domain expertise with the IoT platforms, which is ultimately required to steer and gain value from the data analysis. So this table summarizes the common IoT platforms. Basically, they are the platform where people can develop IoT solutions and applications. So now let's look at the typical representative IoT technologies. There are many enabling technologies contributing to the rapid development and implementation of IoT systems. This session presents and discusses three technologies, including the cloud computing, virtual reality, and big data analytics that promise to improve IoT-enabled manufacturing services. So cloud computing, we talked about this before. Cloud computing provides internet-based computing services, including data storage, data management, KPI computation, data visualization, and data analytics, among others. So if you're using Google Drive or OneDrive, actually that can be considered to be part of cloud computing. There are three broad categories of cloud computing services. So you should be familiar with these names: infrastructure as a service, platform as a service, and software as a service. We recap the definition of each of them here below. Cloud computing allows IoT systems to gain ubiquitous access to share computing and storage resources, thereby overcoming the disadvantage of limited computing resources and storage capability in the things. In addition, the integration of cloud computing with IoT offers services such as machine learning and data analytics over the internet, supporting intelligence and decision-making in different contexts. The second technology we would like to discuss is virtual reality and augmented reality. The integration of virtual reality and augmented reality with IoT systems is conducive to asset utilization, labor training, root cause diagnosis, and maintenance, among others. VR enables a person's physical presence in the virtual world and simulates human interactions with virtual objects. So if you play with Oculus, the virtual reality headset or the Samsung headset, you should have those experiences. VR has been used widely in digital design, workforce training, and predictive maintenance. However, AR augments the real-world physical environments with computer inputs such as instruction, sound, video, and graphics. If you play with the mobile app Pokemon Go, so you can overlay a Pokemon into the street, the real street. So that's how AR looks like. AR enables close interaction between the physical world and the cyberspace, thereby enhancing the user experience and knowledge about the connection between smart things and the network, human operators, and other things. The next technology is big data analytics. IoT sensing leads to big data with the following characteristics: high volume, high velocity, high veracity, and high variety. Well, we talked about this in an earlier chapter. A large number of things generates huge amount of data in real time. The challenge with manufacturing data is that it can be big in terms of variety and veracity. Variety, we know that it covers different sensor values, including the force, the acceleration, the temperature. They are different, right? The velocity is particularly important in the IoT paradigm, given the uncertainty of the statistical models. However, the manufacturing industry is not well prepared for changes in the quest of data-driven knowledge. Big data analytics provide efficient and effective methods and tools to handle large-scale IoT data for information processing and manufacturing process control.